All right, now this section is quadratic models. So we're going to be using quadratics, obviously. We might be writing equations for quadratics. We might be using an equation for a quadratic. And in general, it's going to be not in a traditional way. So think about the basic parts of a quadratic. You've got your minimum or maximum that happens at the vertex. The y-intercept is where your x is equal to 0. The x-intercept is where your y is equal to 0. And the reason that I mentioned that is that that information could help you write an equation from given information or even from a graph. Or if you have the equation, knowing those things might help you know what to do with them. For example, if you have a story problem and they're asking you for some type of initial value, what's the height at the beginning, blah, 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 that's going to be your y-intercept. So that means your x value is 0. If you many times you're looking for minimums and maximums. If that's the case, you're looking for a vertex. And then also a lot of times you're looking for where that y value might be 0. Where does something hit the ground? That's going to be where it has a height of 0. That's going to be an x-intercept. Now, this one's a little bit different. This is not really a story problem, but this is something that I saw in a lot of other books and in some other former test questions. It's not necessarily something that was in your homework, but something that you do need to be able to do. So in this case here, we're looking for the equation for the graph. And I don't have a lot of information here. I do have the vertex. I do have this point right here, and according to this picture, that point would be -3, 0. Now that's an x-intercept. Now an x-intercept is going to be symmetric to the axis of symmetry or to the vertex. So if we think about drawing this axis of symmetry here, this vertex or this intercept right here is 4 away from my vertex. So that means that I'm going to have an intercept on this side 4 away from my vertex. So that would be the point 5, 0. So now I have 3 points on my parabola. Now, to write an equation for this, there's lots of different ways that you could do this, but at least in this situation, which is most of the situations that I saw in my kind of research, if you want to call it that, you had intercepts, or at least one intercept, and you could find the other one based off that. So that being said, I could write this factored, because remember, you get those intercepts by factoring a lot of times. So if that's the case, think about having this equation here. Now, this is not something that's given to you. This is just something that you need to think about, the fact that you could do this. If you were to take this equation and set it equal to 0, you would end, A is a constant in this case, you would end up with intercepts of x sub 1 and x sub 2. So I'm going to take my intercepts right here of -3 and 5, and I'm going to write them as factors. So that would be x minus -3, or plus 3, and x minus 5. Think about the fact that if you set those equal to 0, you would get -3 as an intercept, and you would get 5 as an intercept. Okay, now, how does this help me? Well, that would be an equation if I knew what a was. It's not in the normal form that we're used to seeing, but it would be. So how do I figure out what a is? Well, I've got a point right here. This point is an x and a y. Plug in that x and y. And then solve for a. So this is going to be a times 4 times -4, a times -16, and then a is not 4. You have to divide both sides by -16. A is going to be 1/4, or 0.25. So you could write the equation y equals 0.25 x plus 3 x minus 5. Or if they insist on it being in your kind of standard form, which would be this, multiply it out. So go ahead and multiply the x plus 3 and the x minus 5. So that's going to be x squared minus 2x minus 15. And then multiply it out. So that's going to give me y is equal to 0.25 x squared minus 0.5x minus 3.75. So this would be an acceptable answer. So would that. If they don't specify, stop there, because that's a lot easier. Okay, next. This one is more kind of your traditional story problem. And we talked about one like this yesterday. So Andrew shoots an arrow off of a jetty. The arrow's height above the water t seconds after being shot is given by h of t is equal to negative 2t squared plus 6t plus 3 meters, where t is greater than or equal to 0. That should be obvious, but a lot of times I do put that in there just as a precaution, I guess. So how high above the water is Andrew when he shoots the arrow off the jetty? Okay, so when he shoots the arrow off the jetty, it's when time starts, and time starts at time 0. So in this case, t is equal to 0, which you really don't even need to physically plug in. You can look at it and see the answer is 3 meters. That's an initial value. That's your y-intercept. Okay. Now, how high above the water is the arrow after 1 second? Okay, well, in this case, t is equal to 1. So negative 2 times 1 squared, 6 times 1 plus 3. That's going to give me 7 meters. Okay. Now, how long does it take for the arrow to reach the maximum height? So I only did one of these questions just because I wanted to talk about other things too, but you're going to see quite often them talking about maximizing your profit. You want to get the most, you want to make the most TVs that'll give you the most profit. Anytime it says something about the most, maximum, the least, minimum, that's going to be a vertex. Okay. So in this case, we're finding the vertex either by graphing or by using our negative b over 2a. I'll do a graphing one here later, but I'm just going to go ahead and use negative b over 2a. So in this case, my b value is 6, so negative 6. My a value is negative 2. Negative 6 over negative 4 is 1.5. So they wanted to know how long does it take? That's how long it takes. Now, how far above the water is the arrow at its highest point? Well, the highest point happens at 1.5 seconds, so I'm going to plug that back in to find out what that highest point is. So t is equal to 1.5, so that's going to be negative 2, 1.5 squared, 6 times 1.5 plus 3, and that gives me 7.5 meters. Okay. How long does it take for the arrow to hit the water? Okay, so if the arrow hits the water, the height above the water would be 0. So I'm going to set this thing equal to 0. Okay, so again, we've got 2 options here, 3 options of how we can solve this. This is not factor. I could use the quadratic formula. I could use the calculator app, the PolySimil 2. Or I could graph it and I can find out where it hits. Let's see. Let's use the app, and maybe let's look at the graph too. So if I use the app, I'm going to go to on my calculator number 4, and I want to use number 1, and I'm going to put in. Sorry, I was hitting enter instead of number 1. Okay, so I'm going to put in negative 2, 6, and 3. Now remember, you should have an answer that makes sense. We're talking about time, so we shouldn't have a negative. So the answer to 3 sig figs would be 3.44. Now, just to show you that we could get that by looking at the graph too. If I look at the graph here, sorry, I have to quit this first. Look at the graph. That's going to be negative 2x squared plus 6x plus 3. I'm going to make sure that I have a standard viewing window here. Okay, so just a couple things to point out. Here is my, and again, sorry, it won't let me draw anything. But up here at the top, that's going to be my vertex, so that's going to be my maximum height. And then here is where it's going to hit the water. It also hits the water over here, but that's going backwards in time. So if we want to use, and we'll just go ahead and do both of them since we're here. If I wanted to find the vertex, the maximum, okay, in this case that is a maximum. Sometimes it's a minimum. You're going to hit enter on the left-hand side of your vertex. Doesn't matter how far to the left, it just has to be to the left. Hit it on the right. I didn't necessarily mean to go over that far, but, and then where do you think the maximum is? I think it's about right there. And okay, we talked about this yesterday. Probably it's 1.5. So you could plug in that actual 1.5, or you could use the formula, the negative b over 2a, to back that up. Okay. Now, as far as where it hits the ground, go back to calculate again. This time we want to look for a 0, not intersect. Intersect's going to be where two graphs intersect each other. So that's going to come down here. Not so close. Okay, left-hand side of where I think it crosses. I think it crosses at about 3.5, so this would be the left-hand side of that. Okay, then we're going to come down here and hit enter here, and then about right here. Okay, I'm going to hit enter. And so the y equals negative 1e to the negative 12, that's essentially 0. On the other side there, 3.44, that's the number that I got before. So that's pretty safe to assume that that is your actual 0, your x-intercept, again to 3 sig figs. Okay. Now I'm going to add in an f that you're not going to see on the screen here, that I'm going to add in before I copy this to give to you, because as I was doing that and I mentioned how we were not using the intersect, I forgot that I did want to go over with you again how to do an intersection. So let's say that Andrew shoots off this arrow and then somebody else shoots off a gun, I guess. So we want to find out when the bullet would maybe hit the arrow. All right, and then let's say that this person that is shooting the gun does something very unsmart, we'll say, and they decide to shoot this gun straight up. So the equation that models the path of the gun is this. And I want to know, when is the gun going to intercept the arrow? So what I would do is I would take this right here and I would graph it, and I would take the equation we've been dealing with here and I would graph it. Now let me go back to this equation here. This would be given to you with t's, because it'd be talking about time also. Okay. And then let's go back to the calculator. Okay, so now we're going to put the equation for the models the bullet in the gun. So that's going to be x squared plus 5x minus 4. I don't know if I've ever actually said this or not, but the fact that the equation uses t's and the fact that you put in x's makes absolutely no difference. Okay. All right, so now I'm going to hit graph. And here comes the bullet. Okay, where do they intersect? Well, it intersects pretty close to the maximum there. I didn't necessarily mean for that to happen, but here we go. So find the intersection. We're going to go to calculate intersect. So this one's really easy to use. We're going to go to where the two graphs intersect, which looks to be about right here. And I'm going to hit enter 3 times. 1, 2, 3. And there's my answer. So they would intersect at 1.70 seconds, which is not very long, obviously. Okay. All right. Okay, next, you've seen this type of problem before. When we did this before, though, we were doing it with calculus. In this case, we're going to do it a little bit differently, okay? So we have a farmer that has 20 meters of fencing to create a rectangular enclosure next to his barn. 2 sides of the enclosure are equal lengths. So we're going to write, first of all, a linear equation for L in terms of W. So for this enclosure, I have 20 meters of fencing, so that's all I can use. So being that I have the barn on the left-hand side, I don't need to put a fence there. I'm going to add my 2 widths together and the length, and that's going to be 20. So W plus L is 20, or 2W plus L is 20. Now when it says to write an equation for L in terms of W, that means they want you to solve it. So that's what they're looking for. Okay. Now write a quadratic equation for the area in terms of W. Okay, so my area would be W times L, or length times width, whatever you want to do there. So I only want the equation to have a W in it. That's what in terms of W means. So I'm just going to take this right here, this length, and replace it. That way they're all W's. So W, 20 minus 2W, 20W minus 2W squared, and negative 2W squared plus 20W. Now, you don't necessarily have to rewrite it, but that's going to be helpful for the next part of the question. And technically, you could even leave it like this. That is a quadratic, but I think they would probably want to see the squared. So I would go ahead and multiply it through. Okay. Now, find the dimensions of the enclosure. I want it to be, and actually I don't know that it really specifically says this, but I want it to be the biggest enclosure that it could be, which I think is, you know, pretty usual for this type of thing. I mean, I guess there could be a specific size you would want it to be, but he wants to get the biggest bang for his buck, so biggest enclosure that I can make. Okay, so that being said, if I want the biggest dimensions, W is part of my biggest dimension, biggest area, I want to find the vertex. And really that's all it is. Anytime you are dealing with a parabola and you want something to be the biggest, it's going to be a vertex. So I'm going to find the vertex of this. So I'm going to use just algebra, negative b over 2a. So negative 20 over 2 times negative 2, negative 20 over negative 4 is 5 meters. Now that's my W, because in this case W was like my X. So I want the dimensions of the enclosure, not just the width, so I'll have to plug that back in to find the length. So use the formula from right here. So that's going to be 20 minus 2 times 5. 20 minus 10 is 10 meters for my length. So this is a 5 by 10 meter fence, or enclosure, I should say. Okay. Now find the area of the enclosure. I'm just going to multiply those together. So 5 times 10, literally, is 50 meters squared. All right, last part. 6 identical adjacent pins are found as shown below using 1,800 meters of fencing. Explain why 9x plus 8y is equal to 1,800. Okay, so the fencing has to do with perimeter, but it's the perimeter of all the spaces. Now, you might say, well, let's find the perimeter of 1 and take it times 6, but you've got areas that are duplicated, okay? So that being said, if we just look at this here, we have 9 places that are X, and we have 1, 2, 3, 4, 5, 6, 7, 8 that are Y. And really it's just a matter of putting that into words. So you can say there are 9 sides of X and 8 sides of Y that equal 1,800 meters of fencing. That's it. Okay. Now show that the area of each pen is A equals negative 9/8 x squared plus 225x meters squared. Okay, so to find the area of a pen, the area is going to be x times y. Well, notice this equation does not have a y in it, so I want to get rid of the y. So I'm going to take this equation right here, because the area is based off this perimeter. I mean, I only have so much fencing that I'm using here. So I'm going to take that equation, solve it for y, and then plug it into that area. So I'm going to go ahead and start solving that equation. So I move the 9x to the other side and then divide everything by 8. So now that's going to go right there. Area is x times negative 9/8 x plus 225. So the area is negative 9/8 x squared plus 225x, which is what they told me it was. Okay, and finally, if the area is to be maximized, what would be the dimensions of each pen? Okay, so again, we're using the vertex here. So we're going to find the vertex of this. Okay, that's going to maximize that area. That'll give me the x part, and then I can plug that back in to find the y part. So very similar to what we did in the last one. So to find my vertex, x is equal to negative b over 2a. Now, I must say that in this one, I was a little leery of doing this, thinking, ugh, that's not going to work out very nicely, but it did. If it didn't, you could probably, it's probably going to not work out nicely when you graph it either way. If I take 2 times negative 9/8, that's actually negative 2.25. So then that turns out to be 100 meters for my x. Now, plug that back into the red formula up there to come up with what my y is. So 9 times 100 plus 8y is equal to 1800. And I get that y is 112.5 meters. Now, if you're a tester, you might want to make sure that you actually write this out as your dimensions and put your actual units on there as well. Sorry, it's a mind of its own right now, panel. All right, well, it's not going to there we go. Okay, I was just going to fix that. There we go. Okay, so that's it. Actually, I was getting ready to stop the recording and then stop to think for a minute. So I know that I didn't do an example of everything that you will see in your homework. If you get stuck, as always, look at the solutions, and then if you can't tell from looking at the solutions what they did, why they did it, definitely let me know. Also, look at the examples in the book. I don't use any of the same examples that the book does, so that you have those as extra examples. Always look at those as well.